In the next part of our lesson, we're going to apply the one-to-one property of logarithmic functions to solve equations. The one-to-one property of logarithmic functions looks very similar to the one that we've had for exponentials, but we're going to look at it in terms of logarithms. At this point, I want to hopefully connect the dots between these relationships between logarithms and exponentials and this whole concept of one-to-one functions. So what I'm going to do is I'm going to take a simple exponential function, y equals 2 to the x. We're going to graph the ordered pairs, x and y. Well, if we put in a -1, we get a 1/2 back. If we put in a 0, we get a 1 back. If we put in a 1, we get a 2, and we can graph more ordered pairs, but that's really all that we need. Now, what I want to emphasize on these, when you have an exponential function, you're going to feed it exponents. We know that we can put in a -1 in for x, and it gives us a 1/2. We put in a 0 for x, and it gives us 1. So we're really putting into the function exponents, and then we're getting in return things that we call antilogs. So we feed in an exponent of a -1, and we get back an antilog of a 1/2. We feed it an exponent of 0, it gives us an antilog of 1. We feed it an exponent of 1, it gives us an antilog of 2, so 1, 2. If we fed it an exponent of 2, it would give us an antilog of 4 back. So just, that's 2, we're 4 up here. So we're going to get a graph of an exponential that looks like this. Now, earlier in the presentations, we said that this was going to pass the horizontal line test for sure. Just to grab a decent line here, no matter where I draw that horizontal line, it will pass that, so we call it a one-to-one function. The nice thing about a one-to-one function is for every input, there's a unique output. Well, that's nice when we come back to thinking about the inverses, because now the inverse of an exponent is a log function, or a logarithm. So the inverse of an exponential base 2 is a logarithm of base 2. Now the way these are set up, since they're inverses, we got this concept. What should happen to these ordered pairs if we graph the inverse? Well, we know that the domain and range switch, so that means it forces our x and y's to change. So now what comes in here are your antilogs, and what you're going to be finding are your exponents. And really that's the whole purpose of logarithms. Logarithms are designed to help us find the exponents that we raise antilogs to, or numbers bases to get the antilog. So when we look at this, we're going to be feeding this a 1/2. And if we looked at just this statement here alone, it would say, if I put in a 1/2 for x, we're saying, what do I raise 2 to get a 1/2? And that would be a -1. Then we take the ordered pair 1, 0. We know it has to flip. It's got to be 1, 0, but in the context of this, we're saying, what if we put in place of that x a 1? It's saying, find the exponent I raised 2 to get a 1, and that exponent is 0. Then the next one is, the ordered pair 2, 1. So we have to switch the ordered pair around. So we feed it an antilog of 2, and what do you raise 2 to get a value of 2? And that is 1. The exponent is a 1. So the idea is we switch the roles of domain and range, and we feed logarithms antilogs, and it gives us the exponent. Or in the other case with the exponential curves that we have here, we feed it exponents, and it can quickly tell us the antilogs. Well, the bottom line is, if I switch the last order pair around 4, 2, we can get a graph of a logarithmic graph as well. So the order pair 1/2, -1, so somewhere in this area. Then we have 1, 0, which is here. We have the order pair 2, 1, which 2, 1 would be somewhere in this area, and 4, 2, that's 2, 4. We got to go up 2, so it'll be somewhere in that area, and this will be our log function. Okay? It should be a mirror across the line y equals x if it's drawn perfectly. So we have this idea that logs are inverses of exponentials. But here's the idea of the one-to-one function. On the green graph of the logarithm, if we look only at the green logarithm graph, it passes the horizontal line test, which means it is a one-to-one function, which means for every antilog, there is a unique exponent that's going to be mapped to it. So if I have an antilog of a 1/2, which means I'm going to come over here, 1/2 unit to the right, then there's got to be just one and only one exponent that I can raise 2 to get that, which is a -1. So that's why the ordered pair that corresponds 1/2, -1 is on our graph. And just one more example of that same idea. If we feed it an antilog, we're saying, what is the exponent I raised 2 to? So if I go 1 unit to the right, it's saying, what is that exponent I raised 2 to get 1? Well, the exponent we raised 2 to the 0 power is 1. So that's why the ordered pair 1, 0 is on the graph. But there's only going to be one exponent. The idea of 1 to 1, there's only one. So we're going to apply this property in more detail down here below. So our job here is simply to solve exponential equations using the 1-to-1 property. As you notice, these two properties, log of base 6, log of base 6, coming back up here, if the log bases are the same, log base b of x and log base b of y, if these exponents are identical, because logs are really exponents, then the only way they can be equal is if their arguments are the same, if x and y are the same. So if we're going to find the exponent of 2 to the x, and it's equivalent to the exponent of x squared minus x plus 2, and the bases are the same, then these arguments have to be the same. So what we're going to do is, if we get the same base, log base 6, log base 6, we equate the two arguments, 2x and x squared minus x plus 2, and then we solve those. So that's the application of the 1-to-1 logarithmic functions. And it's just saying that there's no way that these can be equal unless x and y are equal, which are your arguments. So, okay, so let's solve this resulting equation. This time it's a quadratic equation. So to solve a quadratic, our context changes a bit. Our strategy becomes get one side equal to 0. So 0 equals x squared. We subtract 2x, and now we have negative 3x, then plus 2. Now we have some choices. I think I can factor this, so I'm going to use the factoring method. Factors of x squared are x and x. Factors of 2 that'll give me a 3 would be minus 2, minus 1. That's the correct factorization, so now we use our zero factor theorem. The only values of x that I can use to get exactly an answer of 0 are positive 2 and a positive 1. So our two answers that we believe would work would be positive 2 and positive 1. Okay? In the second example, very similar strategy here. We have a log base 12, log base 12, log base 12. So they're all the same log base. So coming up here to our 1-to-1 property of logarithms, if we have the same log bases and we can get them as a single log expression, then their arguments have to be the same. Well, the log base 12 of x plus 3 is just the way we want it. It's a single logarithm with a single argument. Equals. But over here we've got two log statements, but we can apply some of our log properties to help us with this. The log of the sum can be written as the log of a product. So log base 12 of 4 times x. So we're going to use the log properties that we studied in lesson 3 to help us solve these. Now we have this set up so that we can use our 1-to-1 property of logarithmic functions. If the bases of our logarithms are the same, then the arguments are going to have to be the same in order to find those exponents. So x plus 3, our exponent that we raised 12 to has got to be the same as the exponent we raised 12 to on these. The only way we get the same exponents is if the arguments are the same, and that's the key idea here on this logarithmic problem. So the argument x plus 3 must be equal to 4 times x. Solve the linear equation, subtract your x, so you got 3 equals 3x, and x equals 1. So the idea is get the same log base. If they're in the same log base, try to write it as a single statement. You're probably going to have to use some of your log properties, either the product, quotient, or power rule to get them there so that you have one base. So equate their arguments if the bases are the same. Very similar strategy what we looked at for exponentials.